Okay, so we start a new lecture today, lecture number 17. In this lecture, we'll talk about solid solutions in the metallic context and alloys, which are formed by mixing one or two or more elements. So let me just recap the initial, the last lecture first. So in the last class, we learnt about interstices. Okay. Interstices are nothing but voids which are present in the crystal structures, and there are two types of voids that we are concerned about. One is tetrahedral and second is octahedral. So tetrahedral void is characterized by four-fold coordination because it's a body with the four corners. So as a result, the impurity that sits inside has four neighbors, whereas octahedral is six-fold coordinated void. And if you have a regular tetrahedra and regular octahedra, as is the case in case of FCC and HCP structures, then the size of an atom that can fit in tetrahedral void is 0.225 of radius of the host atom. This is without distorting the tetrahedral void. Okay. Similarly, R oct is 0.414 R. So this is the maximum size of the atom that can fit in octahedral or tetrahedral impurities without distorting the octahedra or tetrahedra. And this is in case of FCC or HCP. And we also saw that in FCC HCP you have two tetrahedral voids per atom and one octahedral void per atom. Things are different for BCC. You don't have a regular octahedra or tetrahedra, but you do have octahedral and tetrahedral voids, and whose location and numbers are different. So this I showed you last time in a geometrical fashion. So you were asked to count the numbers of octahedral and tetrahedral voids in BCC. So I will leave it to you. That is a home exercise. That is, what is the location of tetrahedral and octahedral voids in BCC structure, and what is their number. Okay. And you can also calculate what is the size of atom that can fit in there. You have to be a little careful there because the sites of tetrahedra and octahedra are different, they are not regular. As a result, you need to look at the minimum size, okay, the minimum side length. So now in this lecture, we will talk about solid solutions, okay. Solid solutions are just like liquid solutions, they are solution of two or more elements into I think it is too small, okay, solution of two or more atoms into each other. So what basically what does it mean? So you have a lattice of some structure, let us say some element, or let me just first draw the 2D diagram without getting into 3D. So you have these atoms of host lattice, okay. Now of course this is looking very dilated, but it is not that dilated in reality. So the impurity atom can go either here, a smaller impurity atom, or the impurity atom can go here. The question is, how do they arrange? Is there a way in which they are arranged? So in some sense, although in some sense solid solutions are just like liquid solutions, analogous to such as sugar in when you mix two liquids, or sugar in water or salt in water. So salt molecules dissolve in the water, or sugar molecules dissolve in the water. But since water itself is an amorphous structured, or it doesn't have periodicity, where atoms go is also of little consequence, and water is generally loosely structured phase. As a result, the impurity atoms, salt atoms or some other atoms have plenty of spaces to go into. However, as you notice in case of salt as well, when you put so there is a saturation limit beyond which excess salt doesn't dissolve into the liquid. You can see that the excess salt just remains as solid within the water, because the empty spaces within the water phase are already filled, so it's saturated. So then you go beyond the saturation. Similarly with the sugar and anything else. Same thing happens with solids as well. Solids also have they can only dissolve only a certain amount of let's say solute. So you have solute and you have solvent. So solvent is the host phase and solute is the impurity phase. So they can only dissolve a certain amount of solute in most cases. Okay, there are some cases in which two elements can be put into each other with to either end, and they still remain the same single phase. In solids, what happens is that since atoms are periodically arranged, sometimes you will see structures in which the impurity atoms also adopt structures which are ordered, and they give rise to structures which are ordered structures rather than disordered arrangement of solute in them. So there are various type of solid solutions. We will define them in now. So first solid solution is called as substitutional solid solution, and second solid solution is called as interstitial solid solution. So substitutional solid solution basically means that the solute, or you can say impurity atom, goes to host atom site. So it replaces it occupies the same site as the host atom. However, the manner in which it can do that could be random. So it can randomly go anywhere, or it could be ordered. So this will be determined by various factors. Okay. So for example, thermodynamics plays an important role. The entropy of substitution, configurational entropy will play an important role in determining where we'll go, and temperature plays a very important role. So it's a combination of enthalpy and entropy and temperature which will determine free energy of which structure will be minimum, whether it will be. So you know that G is equal to delta G is equal to delta H minus T delta S. So there is an enthalpy of mixing, there is an entropy of mixing, and then there is a temperature term. These three terms together will determine whether the substitution will be random or whether the substitution will be ordered, because in the end the free energy has to be minimized. Okay. So I will not get into the details of free energy of mixing, but I will recommend you to go through any basic book on thermodynamics such as Porter, Easterling, phase transformations in materials. The first chapter of that book, first or second chapter of that book is very useful to understand mixing of two elements. So, and the second solid solution is interstitial solid solutions, and again interstitial solid solutions. In this, the interstices may go to tetrahedral site or octahedral site. So, depending upon the size of the atom and the structure of the host phase, whether it is FCC, BCC or HCP, the impurity atom may decide to go to any of these sites. So, let me give you now some examples of the manner in which your solid solutions may form. So, for example, let me make a little closer structure so that it's close enough, right? Okay. The impurity atom, suppose if it goes, so let us say if impurity atom is so in this case, do you see any periodicity in random arrangement or ordered arrangement of impurity atom? So, this is let us say your B atom and this is your A atom. So, A is the host phase and B is the solute. In terms of chemistry, you call it as a solvent phase, okay, host lattice. So, this is basically a random solid solution, a random substitutional solid solution. Then you may have other example of so what I do now is oops. There is one extra so here now you can see that your solid solution is random and you can actually construct a lattice here, but your lattice has changed now, okay, because if you remember your primitive non-primitive lattice concept, the lattice in this case is no longer the small blue square, rather it has become a the bigger this has become the lattice, okay. So, this is called as your ordered substitutional solid solution. This typically happens when the impurity concentration is a little larger. So, random solid solutions form at lower concentrations typically, and where it is within the solubility limit, and ordered substitution solid solutions typically form at higher concentrations and they form different phases altogether, okay, different structure altogether. So, I will show you some examples just in just a minute, and the interstitial example could be like this. Okay. So, your interstitial atom may go here, for example, somewhere randomly. So, these are your interstitial sites. Now, interstitial sites in reality may lead to distortion. So, the atom may be slightly smaller or slightly bigger than the interstitial site. So, it may create tensile or compressive stresses depending upon what size it has. So, in real situations they do create stresses. Similarly, in substitution solid solution they do create stresses because the size of the atom is not going to be exactly similar, there is going to be some difference. So, whether it is a difference of 1%, 5% and 10%, that will determine eventually whether solid solution will form or not. But if the solid solution does form, then there are stresses in the structure. So, this is called as your interstitial solid solution. You can have ordering at the interstitial sites as well. You can have ordering at the interstitial sites as we will see in case of, for example, silicon carbide or zinc sulfide, but it typically happens in case of ionically or covalently bonded solids. In case of metallic solids, typically interstitial bonds, interstitial solid solutions are random in nature. So, interstitial sites are randomly occupied, but we do have intermetallics, we do have ordered solid solutions in which you will have ordering of impurity at even at interstitial sites, but it is typically more common in compounds where covalent or ionic character is stronger. So, the real examples of these two are, for example, copper zinc is an example of substitutional solid solution. Your copper nickel is another example of substitutional solid solution. Copper tin is also an example of substitution solid solution. So, these are some examples of substitution solid solutions. Your interstitial solid solutions is carbon in iron is a interstitial solid solution. This is a very famous example of a metallic alloy containing, so this is basically steel, right? Steel has a ferrite phase which is alpha ferrite, alpha phase, or rather let me call it alpha iron, okay. Alpha iron is BCC structured phase, and with BCC iron with carbon in, it's become very complicated, let me just, so it's basically BCC iron with carbon atoms in interstitial sites. Okay. So, these are some example of substitutions. There are plenty of more examples in metallic systems because most metals are impure. Then even if you say it's 99.99% pure, I mean there is 0.1% impurity sitting there, and that impurity may go to interstitial or substitution sites. So, let us just look at the example of copper zinc alloy first. Okay. Now, this is with the Cu to Zn ratio of 50:50. Okay. So, above 470 degrees centigrade or so, it makes a BCC structure. You can see that the structure is not same as copper or zinc, it makes a BCC structure which is a disordered BCC structure. Below 470 degrees centigrade, it makes a ordered structure. So, below 470 degrees centigrade, it looks something like this. So, these are your atoms. You do not know which one is copper and which one is zinc. So, there is an equal probability of, so this is above 470 degree centigrade. So, it is possible that this atom will be copper, some other will be zinc, it is just that 50% are copper, 50% are zinc. So, each atom is characterized as 50% copper and 50% zinc, because there is equal probability of occupation of two sites. So, as a result, this is a disordered structure and it is a BCC structure, because each atom is 50% copper, 50% zinc. Below 470 degree centigrade, what happens is that there is now a specific preference for sites. So, this is copper or zinc, whichever, this is zinc. Here it's here, so you can see that copper makes one sublattice, zinc makes another sublattice, and both of these sublattices are cubic in nature, primitive cubic in nature. So, these are two interpenetrating cubic lattices of copper and zinc into each other, which are very ordered. So, this is below 470 degree centigrade, and why this happens is that if you look at this case where there is a random distribution of copper and zinc, there is no preference for copper-copper bonds or copper-zinc bonds or zinc-zinc bonds. Everybody is happy with everybody. Copper is okay if its neighbor is copper. Copper is also happy if its neighbor is zinc. Zinc is also okay with copper being a neighbor or zinc being a neighbor. So, there is no preference for any particular kind of neighbor. In this case, below 470 degree centigrade, copper prefers to have zinc as a neighbor and zinc prefers to have copper as a neighbor, because this changes the enthalpy. Enthalpy is depending upon the number of nearest neighbors, type of nearest neighbors. So, this is determined by thermodynamics, what will be stable. So, this is a disordered solid solution, this is an ordered solid solution. In disordered solid solution, you cannot pinpoint and say that this is copper atom or this is zinc atom. There is a probability, okay. But in case of ordered structure, you can make a difference, and this is very clearly seen in X-ray diffraction pattern. When you do the X-ray diffraction analysis, as I will show you later, X-ray diffraction will show you a pattern for disordered structure same as a BCC material, which is very different for a cubic structure, primitive cubic, which is for ordered copper, because here you will see two superlattices, one of copper, one of zinc. So, they will have their own effect on the X-ray diffraction. So, now the question that arises is, so
can we have this disordered structure at room temperature?
Of course, yeah, you can have a disordered structure at room temperature. Many dilute solid solutions are disordered. This is at very high concentration, this is 50-50, but if you have, let us say, 1% zinc in copper, or for example, copper nickel, very good example, copper nickel all the way it is FCC. So, you cannot distinguish which is copper, which is nickel. So, copper nickel, for example, is like this. Copper is FCC, right? So, at any concentration, each atom is mixture of copper and nickel. The probability of each site being occupied by copper and nickel is determined by their fraction. So, if it is copper nickel 50-50, each atom is 50% copper, 50% nickel. I mean, it is not realistically it will be either copper or nickel, but probability wise it is 50% copper, 50% nickel. If it is 25% copper, 75% nickel, it will be 25% copper, 75% nickel. So, there is a, so this is a disordered solid solution which remains FCC even at room temperature, no matter what the fraction of two elements is, okay. So, let me, so these solid solutions, when you make the solutions, solutions are called as basically alloys, and the atoms are put in intentionally to improve the properties, second phases are, or other elements are added. Okay. So, it is intentional in many cases. In some cases, of course, it is unintentional because you cannot remove the impurity, but in most cases it is intentional. For example, so examples are steel, which is iron carbon alloys with up to 2% carbon. Okay. Then you have brass. Brass is copper zinc alloy up to about 50 weight% zinc. This is again 2 weight%. Okay. And then you have bronze, which is copper tin alloy, which has up to about 12 weight% tin. Okay. Now, here one thing that is interesting is copper has a structure which is FCC, zinc has which is HCP. Copper again has FCC here, tin has HCP or BCC depending upon, but it is HCP. Okay. So, the question is, what is the structure that the eventual alloy going to take place? Are there any guidelines? Okay. So, there are certain guidelines which are called as Hume Rho 3 rules. Okay. Now, which say that extensive solid solubility occurs may form when number 1, the size difference between two atoms is less than 15%. Number 2, there should be smaller difference in the electronegativity, which means they should not be very far apart in the periodic table, otherwise they will make an ionic bond. Okay. So, there should be smaller difference in the electronegativity. Third is their valences are similar. Now, these are not exactly rules, these are guidelines because there are violations which are there. Okay. But by and large they are followed in most metallic systems. So, and fourth is the crystal structures should be similar. So, when the valences are not similar, then the valence of, so element with higher valence is likely to dissolve in the element of lower valence. That is typically the norm. And if electronegativity difference is large, then instead of making an alloy, it tends to make a compound, ordered compound. It could be, it's called as intermetallic, or it's called as a line compound or something like that. It looks like as if it's an ionic compound, but it's like it has a higher ionic covalent character than metallic bonding because of large difference in the electronegativity. It's called as an intermetallic compound or line compound. So, these are certain guidelines which are to be followed when you form the structures. Deviations typically lead to lower solid solubility. If you have deviations from these rules, they lead to lower solid solubility, which means you cannot dissolve a large amount of impurity in the host phase if there is a large size difference, if there is a large valence difference, if there is a large change in the crystal structure, because they are not compatible with each other as such. So, let me give you some examples. So, the first example, let us say, of silver gold. So, we can see that silver here has FCC structure, gold has again FCC structure, silver has a radius of 1.44 angstrom, gold has a radius of 1.44 angstrom, it has a valence of 1, it has electronegativity of 1.9, it has electronegativity of 2.4. So, this is electronegativity, this is valence, this is size, this is structure, and they make a solid solution which is extended solid solution. Similarly, copper nickel, I was talking about the copper nickel system, and the reason for that is copper is FCC, nickel is FCC. Copper has a radius of 1.28, nickel has a radius of 1.25. Their valences are not similar, by the way. Copper could be +1. Electronegativities are fairly identical, and they make extended solid solutions all the way from copper to nickel. Okay. And then silicon germanium is another system which is very well known system. So silicon, germanium, both are diamond cubic. I will come to diamond cubic structure later on. I have not, but this is basically FCC lattice. Silicon, this is 1.22 radius, this is 1.18. The valence is 4 for both of them. Electronegativity is same. They make extended solid solution. Okay. On the other hand, when you make CuZn, copper is FCC, zinc is HCP. As a result, the solid solubility is limited. You can only put 35% zinc in copper and nearly 1% copper in zinc without making a second phase. Okay. So these are extended solid solutions. Spanning from pure copper to pure nickel, or pure gold to pure silver, or pure silicon to pure germanium, and this is a partial solid solution. It makes a solid solution up to 35% zinc on the copper side, and it makes a solid solution only up to 1% copper on the zinc side. If you are between these two ranges, then they make second phases which are not solid, which may or may not be solid solutions, but they are different phases. Okay, because it cannot accommodate more zinc or more copper in it. Okay.